Good morning, students. So in this week, we will be looking at the chapter on probability. As I promised you in the last class, I'll be starting a new chapter whose name is probability. So before going into the understanding of probability, probability simply means a chance. Something like if I say something like today there is a chance of raining. Today there is chance of maths class. Something like if I say today the team A has a chance of winning at the chances around 0.25, something like that. So that's only probability. Without knowing, you have been using the word called probably. In English, probably today it might rain. So that is only chance. Okay, so that's only called chance. So probability is nothing but chance. So we are giving a mathematical aspect to probability, to chance whose name becomes probability. Okay, so before going into the basics of probability, we should understand some of the basic terms. So before I start, the first term that I'm going to discuss with you is an experiment. An experiment is an action which results in some well defined outcomes. Suppose something like, suppose if I say something like it might rain or it might not rain. Yes, so that is an experiment. So basically we are doing an experiment saying that it might rain or it might not rain. So we know the outcomes properly. Either it's going to happen or it's not going to happen. But if I say something like good, a boy is good or bad, but it's very difficult to judge, right? Because we don't know what is the meaning of good and bad. So in that case, we can't tell that to be an experiment. That is only qualitative. So experiment has to be quantitative, either yes or no. Okay. And also the next topic is a random experiment is an experiment with more than one possible outcomes, and it is not possible to predict any outcome in advance. So example which I am giving out here is tossing a coin whose outcomes are head H and tail T, but whose outcomes we cannot predict. Suppose something like we are tossing a coin. Okay, so its outcome will be either head or tail, right? But we do not know what will be its outcome. So in that case, this experiment is called random experiment. But something like if we already know that tomorrow is Wednesday and we are just predicting which day will be tomorrow, it's very easy to say, right? Because it's going to be Wednesday. So in that case, it will not be a random experiment. So remember, in random experiment, we should not know the outcomes properly. In the sense, what is going to happen, we should not be able to tell it definitely. Okay, I hope you are clear with the concept of experiment and random experiment. So let us understand what is trial. So when a coin is tossed, remember I'm going to give, I'm trying, I'll be able to explain each and every concept using the coin only. I'm going to do that. Okay, a coin is tossed one times, two times, etc. Each toss of the coin is called a trial. So every, suppose I'm tossing a coin, then every toss is called a trial. Okay, so let's understand that is a trial. So we have gone through experiment, random experiment, and trial. Next is if all the outcomes of an experiment have equal chances to take place, the outcomes are said to be equally likely outcomes. What is it trying to say is, suppose if I have a bag full of balls and all the balls are of identical shapes but of different colors. So unknowingly, without knowing, if I just blindly pick out one ball, every ball will have equal chance of coming out, right? So in that case, we call that to be equally likely outcomes. But if I say that the balls are of different size, some is big, some is small, and some is very small. So in that case, we can't call them to be equally likely outcomes because my hand will always reach for the bigger ball, so bigger ball will come first. So in that case, this experiment we cannot call it to be equally likely outcomes. Okay. So I have given on examples also. The outcomes of tossing a coin are equally likely outcomes as both the head and tail have equal chance of coming. Okay. So now I'm coming to the formal definition of probability. I'll be giving one formula. How to use it we'll be discussing now. So if n is the total number of outcomes, that means suppose in the case of if I'm tossing a coin, so how many outcomes I'll have? Two, right? One is tail, one is head. So in this case, number of outcomes will be n will be 2, and outcomes favorable. That means suppose if I am checking how many times does a tail occur. So in that case, if I am getting one tail and one head, so in that case, number of outcomes favorable. Favorable means which is supporting my claim, that will be 1, right? So E is any event that we are considering. Event is also an experiment only. So then probability of happening of event E is denoted by P of E and is given by the formula P of A equals M by N. That is, P of event happening is equal to the number of outcomes favorable to that event divided by the total number of outcomes. Yes, and also remember the collection of all the outcomes is called sample space. Okay, so I hope all of you followed what I am telling. I hope all of you are clear with the concepts that I just discussed with you. We started with experiment, random experiment, trials, equally likely outcomes. Then we looked at the formula for probability of an event, and we looked at sample space. Okay, sample space is basically the collection of all outcomes. Suppose all of you would have played Ludo during this quarantine, excuse me, not quarantine, during this lockdown. All of you would have played this Ludo. In that Ludo, if you see dice, what are the outcomes of that? So the numbers are 1, 2, 3, 4, 5, 6. So the entire thing will be the sample space. Okay, so let us start. Let us take one problem. Okay, I'm taking a coin is tossed. What is the probability of getting a tail ahead? Before going into this problem, let me tell you one thing. All of these things we are going to do it theoretically. Okay, this is not practical approach. Practical approach, we'll be learning it in higher classes, maybe in class 9 or 10. That's called axiomatic approach to probability. Here we are going to do it theoretically. What I'm trying to say by theoretically, it means suppose if I'm tossing a coin, I will always assume that once it will come tail and once it will come head. So I'm not going to assume that every time it will come tail. Okay, so I'm going to assume that once it will come tail and once it will come head. Similarly, in case of a dice, if I'm rolling a dice, I'll always assume that once it will come 1, second time it will come 2, third time it will come 3, 4, 5, 6, like that. Okay, remember that we will always assume it to be like that. So that's why it's called theoretical approach to probability. So in this case, you should always write sample space to be T and H. So one tail, one head. So number of favorable outcomes. Remember, we are going for a tail. Okay. So out of this, how many number of tails I have? One, right? Only one is there. So required probability will be nothing but 1 by 2. As you know the formula is number of favorable outcomes. In this case, it is 1, and total number of events. If you see in the sample space, there are 2, T and H. So my probability will be 1 by 2. So before going, so let us understand what is sure event. Sure event means an event which will surely happen is called sure event. Okay, for a sure event, its probability will always be 1. So let me give you one example of a sure event. Suppose in a group of class 8, so if I want to pick up one class 8 student, I will always be able to pick up, right? So every time I pick up, it will automatically be a class 8 student only. Yes, so that's an example of sure event. One more example which I would like to give you is, suppose you want to predict, if you know that tomorrow is Wednesday and if you want to predict that tomorrow is going to be Wednesday, then the probability of that day happening Wednesday will be 1, because it isn't sure event, because it will always automatically be Wednesday. Okay, so that's sure event. Next one is impossible event. An event which will never happen is called impossible event. Suppose if I come to your class, that is class 8, and I tell you, let me select one student from class 9. Is it possible for me to select any student from class 9? No, right? Because there is no class 9 student in class 8. So in that case, I can say that that event is impossible event. Yes. So for an impossible event E, probability of E equal to 0. Also, one property which we should know is, also probability can never be less than 0 and not more than 1. That is, 0 should be less than or equal to probability of E less than or equal to 1. That means the value of probability will always lie between 0 and 1. It can never be negative and it can never be more than 1. Okay, so I hope this is clear with you. So I'll be very happy if someone can tell me the reason why it always lies between the value of 0 and 1. So let us start exercise 23 that is covering probability. So the first question is saying a die is thrown, find the probability of getting a prime number. Okay, so whenever you start a problem, always write the sample space first. So sample space in case of die is how many numbers I can have in a die. Those are 1, 2, 3, 4, 5, 6. Okay, second one, we should always go for the favorable outcomes. So favorable outcomes in this case is the prime numbers. So let us see how many prime numbers I can have. Number of prime numbers equals to 2, 3 and 5. Remember, we do not consider 1 as a prime number. Always keep that in mind. You will study it in college if you happen to take mathematics, why we don't consider 1 as prime number. There's a theory behind it. So we do not consider 1 as prime number. So in this case, favorable outcomes becomes 3. Yes. So therefore I can say required probability equals to number of favorable outcomes, that is 3, and the total number of outcomes. If you see in the sample space, there are 6 elements, 1, 2, 3, 4, 5, 6. So I can write 3 by 6, that becomes 1 by 2. That is your answer. Yes. So number 2, the question is asking a number greater than 4. So let us see which all numbers will be greater than 4. Number greater than 4 is 5 and 6. Yes. So favorable outcomes, if you see, there are 2. Yes. That is 5 and 6. Yes. So therefore required probability equals to 2 by 6, that is 1 by 3. After this, it's just going to be my just reading out the answers because all of them are very logical, and if you are clear with the concepts, all of this you can do it yourself as well. Yes. So number question, other one we are supposed to find is number 3, a number not greater than 4. So number greater than 4, sorry, number not greater than 4, it will be equal to, oh sorry, I have not written it. I think it should be 1, 2 and 3. Okay, 1, 2 and 3. 1, 2, 3, 4. Sorry, not greater than 4. So I can consider even 4. So I'm going to consider 1, 2, 3, 4. I have not written it. Could you please kindly write it for yourself? So favorable outcomes, if you see, it will be 4. Yes, 1, 2, 3, 4. So therefore required probability will become 4 by 6. If you cancel it by 2, you will get 2 by 3. So that is your answer. Yes, I hope you are clear. So next question that I have is a coin is tossed twice. Find the probability of getting exactly one head, exactly one tail, two tails, two heads. So whenever you are tossing a coin twice, we always assume the sample space to be once it will come, both head will come once, again both tails will come, again tail and head will come, and again head and tail will come. Don't get confused. TH and HT are different. How they are different is, if I consider the first one TH, I'm considering that first coin is showing tail and the second coin is showing head. Okay, and in the second case HT, the first coin is showing head for me, and the second case I am showing it is showing tail for me. I hope you are clear with the sample space. Yes. Okay, so after this I have number of favorable outcomes equals 2. Yes, so therefore required probability equals to 2 by 4 equals 1 half. So number of exactly one tail equals TH and HT. Number of exactly one tail means TH and HT. I can consider TT. Sorry. So required probability equals to 2 by 4 equals to 1 by 2. Yes. So this is how we do the problem. Yes.